This is a treadmill motor. $65 used, often free from a curb, and inside it are permanent magnets and a copper armature. Bolt it to a wheel, put that wheel under falling water, and it produces electricity at 3 in the morning. In January, in the rain, when every solar panel in the county is producing exactly nothing, off-grid households with running water on their land have been doing this for decades, and they will all tell you the same thing. Per dollar spent, nothing on earth beats it. And here's the honest part, stated up front, because almost nobody selling this idea will say it. This works spectacularly on the right piece of land and produces literally nothing on the wrong one. The machine runs on one resource, which is falling water, and it needs both parts of that phrase. Water that does not fall is useless, and a fall with no water behind it is equally useless. Knowing which side of that line your property sits on is worth more than the motor, and I will give you the 2 measurements that decide it, both of which you can do this weekend with a bucket and a garden hose. Let me start with why this matters, because the comparison with solar is not close, and almost nobody frames it correctly. Everyone understands solar. Panels on the roof, sunshine in, electricity out, and it has become astonishingly cheap. But solar has one limitation nobody can engineer away, which is that the sun is not always up. Even in a good location, a panel produces meaningful output for a handful of hours a day, and the industry has a word for the fraction of its rated capacity a source actually delivers over time. They call it capacity factor, and for residential solar, it sits somewhere around 15 to 25%. A creek does not care that it is dark. It runs at midnight exactly as it runs at noon. In December, as in July, through cloud, through storm, through snow, a microhydro installation can run above 90% capacity factor, and that single number is the entire argument. Here is what that does to the arithmetic with real figures. Take a modest setup. 3 meters of vertical drop, which is about 10 feet, and 2 liters per second of flow, which is roughly 32 gallons a minute. That is a creek you could step across. Run it through the standard hydropower equation and allow 50% for real-world losses in the turbine, the belt, and the generator, and you get about 29 watts of continuous output. 29 watts sounds pitiful, but 29 watts running 24 hours a day is 7/10 of a kilowatt hour every single day. Now put a 100-watt solar panel beside it. In decent sun, after losses, that panel delivers around 4/10 of a kilowatt hour a day. Read those 2 numbers again. A trickle of a creek producing 29 watts outproduces a 100-watt solar panel by a comfortable margin over a full day because it never stops, and it gets more dramatic as the site improves. 10 meters of head with 5 liters per second, which is a genuine hillside stream, produces around 245 watts continuous, which is almost 6 kilowatt hours a day. That is a serious off-grid supply running through the night in winter. Without a battery bank sized for 14 hours of darkness, which is the second saving nobody mentions, before the second saving, let me make that output concrete, because watts on a page mean very little until you know what they buy. 29 watts, continuous, at 7/10 of a kilowatt hour a day. Will run a modern, efficient refrigerator for roughly half its daily demand. Or keep a well-designed LED lighting circuit running all evening with charge left over, or handle every phone, tablet, laptop, radio, and router in a household with room to spare. 245 watts continuous at nearly 6 kilowatt hours a day is a different category entirely. That covers a refrigerator, a freezer, lighting throughout a house, a water pump, a laptop, a television, and the general background draw of a modern home without ever running short overnight. For context, the average American household consumes around 30 kilowatt hours a day. So nobody should imagine a creek replaces a grid connection at typical American consumption. But an off-grid household that has already reduced its demand deliberately with efficient appliances and no electric heating or cooking runs comfortably in that 6 kilowatt hour range, and thousands of them do exactly that on water alone. The distinction that matters is that hydro output is continuous rather than peaky. 6 kilowatt hours arriving evenly across 24 hours behaves completely differently from 6 kilowatt hours dumped into 4 hours of afternoon sun, and it is the difference between a system that hums along and one that lurches between surplus and shortage. Batteries are the most expensive part of any off-grid system, and they exist almost entirely to carry you through the hours your source produces nothing. A source that never stops needs a fraction of the storage, and for most off-grid builds, that is where the real money is. So the obvious question is why almost nobody knows this, and the answer starts with the motor. Most homemade water generators fail, and they fail for exactly the same reason. Somebody bolts a car alternator to a wheel, spins it, reads 0 volts on the meter, and concludes the whole idea is nonsense. Car alternators are designed to spin at thousands of RPM under engine power, and critically, most require field excitation, meaning they need an external current fed into their windings before they generate anything at all. At the few hundred RPM, a small water wheel produces. An alternator is close to useless. A permanent magnet DC motor has no such requirement. The magnetic field is already there, permanently, built into the machine, so the instant the shaft turns, it produces voltage. Turn it faster, and the voltage climbs proportionally. There is nothing to switch on and nothing to energize, and the cheapest source of a good permanent magnet DC motor in America is the treadmill. Home treadmills use PMDC motors typically rated between 80 and 260 volts. DC, at 1.5 to 3 horsepower, they are built for continuous duty, and they are given away constantly because the machine around them is bulky, unfashionable, and expensive to move. Check any marketplace listing or curb on bulk collection day. The motor is the valuable part, and it is the part nobody wants. That is the whole reason this particular build exists as a folk method. It is not that a treadmill motor is uniquely brilliant, it is that it is the best generator most people can obtain for nothing. Now, this is not a new idea, and it has been proven at 4 completely different scales. Start with the historical one, which is written across the map of your own country. Before steam, and long before the grid, if you wanted to grind grain, sawboards, full cloth, or hammer iron, you built beside falling water, because falling water was the only reliable motive power there was. Tens of thousands of small water mills operated across America, and that is why so many towns sit exactly where they do. Somebody found a drop in a creek and built a mill, and a village grew around it. Look at the place names near you. Mill Creek, Millbrook, Mill Road. Those are not decorative. They are a map of where the power used to be. The scale of that industry is easy to underestimate now. At its height, America had tens of thousands of working water mills, and in many regions, a farmer was never more than a few miles from one. They ground flour, sawed lumber, carded wool, pressed cider, hammered iron, and drove the machinery of small manufacturing, all from a wheel in a creek. The engineering was not crude either. Millwrights were among the most skilled tradesmen of their era, and the systems they built for controlling flow, managing head, and transmitting power through shafts and gearing were sophisticated pieces of design that ran for generations with wooden components. Most of those sites are still there. The dams have silted up, the buildings have gone, and the creeks still fall exactly as far as they always did. Then the early electrical scale. When electricity arrived, the obvious move was to bolt a generator onto machinery that was already spinning, and for several decades, a great many rural communities lit their homes from the same water that had ground their grain. Small hydro plants powered individual farms, factories, and whole small towns entirely independently, decades before a utility line reached them. Then the developing world scale, which is happening right now and is the most instructive of all. Across Nepal, Vietnam, and mountainous parts of Southeast Asia, tens of thousands of tiny turbines, often called pico-hydro units, sit in streams outside homes, producing a few hundred watts each. They cost very little, they are frequently locally made, and they power lighting, phone charging, and a television in households that will not see a grid connection for decades. This is not aid agency theory. It is a functioning consumer market for water-powered electricity at exactly the scale we are discussing. And then the modern off-grid scale, which is the quiet consensus among people who actually live this way. Ask any experienced off-grid community what the best power source is, and those with water on their land will tell you without hesitation that microhydro beats solar and wind combined, because it runs constantly and needs almost no battery. The only reason it is not universal is that most properties do not have a stream. There is also a pairing worth knowing about because the two sources fit together almost perfectly. Streams generally run hardest in spring and after rain, and weakest in high summer drought. Solar runs hardest in exactly that summer window and weakest through winter cloud. So a small hydro system carrying the constant baseload with a modest solar array added for the dry months covers the year far more evenly than either source could alone, and both feed the same battery bank through their own controllers. Households that run both describe the same pattern. The creek does the quiet, unglamorous work of keeping the batteries topped up around the clock for most of the year, and the panels step in during the weeks when the water drops away. That combination is why people with water on their land end up with far smaller battery banks and far fewer bad nights than anyone running panels alone. So if it is that good, why can you not buy a residential microhydro kit at a hardware store the way you can buy a solar panel? The barrier is not performance. It is paperwork, and here it is genuinely more severe than for any other technology in this series. Water is legally complicated in a way, sunlight is not. In much of the United States, and especially across the western states operating under prior appropriation doctrine, the water crossing your land is not simply yours to divert. It may be legally allocated to somebody downstream who has held that right for a century. Depending on where you live, a diversion may require state permits, environmental review, assessment of impact on aquatic life, and in some configurations, a federal exemption. People routinely discover that the studies and applications cost more than the turbine, the pipe, and the generator combined. Add to that the absence of a consumer product. No manufacturer produces a listed, certified residential microhydro unit for a homeowner to buy off a shelf. No installer network exists, and no appraiser will recognize it as an improvement to your property. So a homeowner who installs solar receives a federal tax credit, a turnkey installation, a warranty, an insurance rider, and added appraised value. A homeowner who builds a microhydro system from a treadmill motor receives none of those things, no matter how well it performs. Nobody banned this. The market was built around panels and batteries, and anything outside that shape is invisible. In a system where credits and certifications decide what gets built, invisible produces the same outcome as prohibited. This channel exists for exactly this kind of straight answer. One honest method a week, and subscribing is how those keep arriving. Now the two measurements that decide everything, and you can do both this weekend for nothing. The first is head, meaning vertical drop, and it is vertical that counts rather than distance along the ground. A stream that runs 200 feet across flat ground has no head at all and will produce nothing. The cheap method is a length of clear hose filled with water. Because water finds its own level, you can leapfrog your way down the slope in stages, measuring the drop at each step and adding them up. A builder's level and a marked stick works, and a laser level or a decent phone app makes it faster. What you want is the total vertical fall between where you would place your intake upstream and where the generator would sit downstream. The second is flow. Find or make a point where the whole stream funnels through one channel, take a bucket of known size, and time how long it takes to fill. A 5-gallon bucket filling in 10 seconds is 30 gallons a minute. Do it several times and average it. Then multiply. More drop and more water means more power. And there are free calculators that will do the arithmetic, but the rule of thumb is straightforward. A few meters of fall with a steady flow produces a genuinely useful continuous supply. And here is the critical instruction. Measure in your dry season, not after spring rain. A creek that runs beautifully in April and vanishes in August will give you a system that fails exactly when you need it. Size everything around the worst flow of the year, and you will never be disappointed. Now the build, and it has 4 parts. The intake is where you take water from the stream, and it is where every real-world system spends its maintenance. A screened box or a small settling pool means you draw clean water rather than gravel and leaves. Screen it properly, both to protect your turbine and to keep aquatic life out. The penstock is the pipe carrying water down to the turbine, and plastic pipe is standard. This is where beginners lose most of their power, because water rubbing against pipe walls loses energy the whole way down. Go larger on the pipe than feels necessary. Keep the run short and straight, and avoid unnecessary bends. Undersizing the penstock is the most common mistake in home hydro and the hardest to diagnose because the system simply underperforms, and you never quite know why. The turbine is the wheel the water strikes. With good height and modest flow, you want a Pelton or Turgo wheel, which is a disc with cup-shaped buckets around the rim, hit by a high-speed jet from a nozzle. The classic home builder's version welds ordinary metal spoons around a hub, and that is not a myth. Working wheels have been built exactly that way for decades. The reason a Pelton design works so well is worth 30 seconds, since it explains the spoons. You are converting the pressure in your penstock into a single fast jet through a small nozzle, and that jet carries all the energy of the entire column of water above it. The cup catches that jet, turns it back on itself through nearly 180 degrees, and lets it fall away with almost no speed left. Because the water reverses direction rather than simply glancing off, the wheel extracts close to all of the momentum available, which is why properly built Pelton wheels are among the most efficient turbines ever designed. A spoon, it turns out, is already a cup with a curved back and a rim, which is precisely the shape required, and that is why the folk version works rather than merely almost working. The nozzle matters as much as the wheel. Too large and you dump water through without building pressure. Too small and you throttle your flow. Most builders make 2 or 3 nozzle sizes from pipe fittings and test each one, which costs a few dollars and is the single cheapest way to find another 20% of output. If instead you have lots of water and very little drop, you want a paddle or propeller design that catches volume rather than speed. Then the generator, which is your treadmill motor, coupled to the wheel with a belt and pulleys. You will need a step-up ratio, since a small water wheel turns at a few hundred RPM and your motor wants considerably more. And matching that ratio to your target voltage is the tuning job that makes or breaks the output. That tuning deserves a proper explanation, because it is the step where most builds either come alive or disappoint. A permanent magnet motor produces voltage in direct proportion to shaft speed. Spin it at half the RPM and you get roughly half the voltage. And build it in stages rather than all at once, since that is how the successful ones get finished. Measure the site first and write the numbers down. Then test the motor on a drill and record its volts per 1000 RPM. Then build the wheel and spin it dry too. Check the bearings and alignment. Only then run water through it with the meter connected and nothing else, and see what the machine actually makes. Every one of those steps costs an evening and catches a problem that would otherwise be buried inside a finished installation. You cannot diagnose. That compares to a solar array of equivalent daily output at several times the price. Before you count the batteries, you will not need. Now the section of the sponsored videos skip, because this has real limits and an honest account owes them the same volume as the praise. The first limit, and it is the one that ends the conversation for most people, is that you need a site. No stream, no drop, no power. A flat pond does nothing. A rain barrel does nothing. Physics is not negotiable, and I would rather tell you that in minute 2 than in minute 20. The second is the intake, which is the actual daily job. Leaves, silt, gravel, and ice will clog it, and every experienced microhydro owner will tell you the machine is reliable and the screen is the chore. Autumn is the difficult season. The third is winter, since intakes freeze, exposed pipe freezes, and in cold climates you are burying line and managing ice for several months a year. The fourth is seasonal flow, which is why I told you to measure in August rather than April. The fifth is that treadmill motors have brushes, which wear, and their bearings were never designed for the side load a belt drive applies. Both are cheap and replaceable, and both are wear items you should expect to service. And the sixth is legal, which I have already covered and which is genuinely the largest obstacle in much of the country. Now the safety section, and there are 3 things here that matter more than anything else on the list. The first is unique to hydro and catches solar people completely off guard. With solar, when the batteries are full, the controller simply stops taking power from the panels and nothing bad happens. You cannot do that with water. The stream keeps pushing, the wheel keeps turning. And if you abruptly disconnect the load, the generator spins up far faster than it was designed to and destroys itself. That is why hydro systems use a diversion or dump load, meaning the controller sends surplus power somewhere harmless, usually a water heating element or a resistor bank, so the machine always has something to push against. Many owners heat their domestic water with that surplus, which turns a safety requirement into a free hot shower. Skip it and you will destroy your generator within days of the battery's filling. The second is electrical. Every component near water needs to be in a properly rated, sealed enclosure, above flood level and correctly grounded. Battery banks need proper fusing, correct cable sizing, and ventilation. Since a large battery can deliver enormous current into a short circuit. And you never connect a home-built generator into your house wiring in a way that could push power back onto the utility lines, because backfeeding a grid can kill a lineman working on what he believes is a dead circuit. Tying into a house is a job for a qualified electrician and proper transfer equipment. The third is the stream itself. A microhydro system takes water at one point and returns it at another. And done properly, it is about as gentle as generation gets. Done carelessly, it dewaters a stretch of creek and blocks fish passage. Screen your intake, leave adequate flow in the bed, and return what you borrowed. The ledger for the whole story then, at typical mid-2026 prices: a treadmill motor, free to $65, a Pelton wheel, $20 to $80, or an afternoon with spoons and a welder. Penstock pipe, priced by the foot and the largest single line item on most builds. A charge controller and diversion load, $40 to $120. Battery, fusing, and wiring, $100 to $300. Total, $200 to $800 for a system that runs day and night. In winter, forever, on a resource that was already flowing past your property. Here's the thing worth keeping from all of it. This country ran on falling water for 2 centuries before anyone strung a wire, and the mills are still marked on the map by the names of the roads. Those sites did not stop working. They stopped being used because plugging into a line became easier than maintaining your own machine, and because today the permits cost more than the equipment. The physics never changed. Water still falls, and a permanent magnet still makes electricity when you turn it. If you have water with drop on your land, go and measure it this weekend with a bucket and a hose. It costs you nothing. It takes an afternoon, and you may find out that the most valuable thing on your property is the little creek you have been walking past for years. Everything this channel has gathered on making power the honest way. The pumps, the storage, the wiring, each with its real costs and real limits, lives in one place, linked right below. And the comments are the missing map. Do you have running water on your land, and have you ever measured the drop? Give me the number if you have one, because half the people reading this are standing on a site and do not know it. As for the machine that moves water uphill continuously, with no electricity, no fuel, and no panel, invented over 200 years ago and still running on farms today, that is on screen right now, same creek, different job. Till next time.